Welcome everyone to this Monash Cybersecurity Seminar. Today we are happy to welcome Arpita Patra, who is currently an associate professor at Indian Institute of Science. Her area of interest is cryptography, focusing on theoretical and practical aspects of secure multi-party computation protocols. Arpita received her PhD degree from Indian Institute of Technology, Madras, and held postdoctoral positions at University of Bristol in UK, ETH Zurich in Switzerland, and Aarhus University in Denmark. Her research has been recognized with a Google AI/ML Research Award and an ASI Young Scientist Platinum Jubilee Award, a Serb Woman Excellence Award, an INEAE Young Engineer Award, and associateships with various scientific bodies such as Indian Academy of Sciences, National Academy of Engineering, and the World Academy of Sciences. She is also a council member of Indian Association for Research in Computing Science since December 2017. And today, Arpita will talk to us about privacy-preserved machine learning, and in particular, how MPC meets machine learning. So thank you, Arpita. The scene is yours.
Thank you, Mohammed. So let me share my slides. So all of you can see my slides, right?
Yep, all good.
All good. Okay. Okay. So thanks. Hi everyone, and thanks for tuning in. And my name is Arpita Patra, and today I'm going to speak on MPC meets ML, privacy-preserving machine learning. So this talk is based on a joint work with Nishat, Mahak, and Ajit, entitled Swift, Superfast, and Robust Machine Learning, Privacy-Preserving Machine Learning, that appears this year's edition of Unix Security Symposium. So let's begin with the outline of the talk. So I will give a very quick introduction to ML, and then I will motivate privacy-preserving ML, aka PPML. We're going to solve PPML using multi-party computation or MPC techniques. So next, we will briefly touch upon the general MPC, followed by the specific model of MPC that we focus on for building our PPML solutions. After that, we will take a bird's eye view of Swift framework, that is all its constituent primitives. And then we will go over the details of Swift multiplication, which serves as the technical core of Swift framework. And in the end, I will talk about the comparison and benchmarking with the relevant works. Okay, so let us begin. So machine learning is one of the fastest growing research domains of today. It has demonstrated its potential in many application domains, such as automobiles, healthcare, finance, and so on. A typical machine learning algorithm is split into two phases, training and inference. In the training phase, some of the data owners, they come together and train a model. And after the model is trained, then the model can be used to predict the output for a new query. And this is often referred as machine learning as a service. And there are several companies such as Google, Microsoft, IBM that provide machine learning as a service. It is well understood in the ML community that the key factor that determines the quality of the model is the amount of data that is used to train the model. The more the data, the better, the more accurate the model is. So this creates a lot of advantage and a huge motivation for various entities to come together and train a model on their joint data. For instance, in the automobiles industry, the competing companies can come together and then they can train a model on their joint data, right? But there is a big barrier. The barrier is loss of privacy of individuals' data. The participating entities are concerned about the privacy of their respective data. So the big question is, can we do collaborative computing without privacy breach? Okay, and the answer is yes. And the specific technique of multi-party computation is meant to do exactly that. So for training, we will use MPC to uphold the data privacy of the data owners. And for inference, we will use MPC to uphold model privacy of the model owner and the query privacy of the client. So let us quickly see what MPC is, right? So MPC at a high level permits a collection of data owners to perform a collaborative computation correctly on their private data without revealing anything beyond the computation output. The distrust in the system is modeled by an adversary, which is centralized, and it can corrupt some of the parties. MPC has been studied for various adversarial and security settings. For instance, corruption-wise, we have semi-honest and malicious adversaries. A semi-honest adversary follows the protocol. On the other hand, a malicious adversary deviates from the protocol arbitrarily. And in Swift, we consider the strongest model of malicious adversary. In terms of degree of robustness, an MPC protocol can offer one of the following 4 properties. The first one is guaranteed output delivery, aka GOD, or robustness. This is the strongest property amongst the 4 that we have here. Here, the adversary cannot prevent the honest parties from getting the output, right? So no matter what strategy an adversary follows, the honest parties are always going to get the output. The next one in the list is fairness. Here, if the adversary gets the output, then everybody will get the output. So this creates an all or none kind of situation. Either all or none of the parties will get the output. Next, we have security with unanimous abort. Here, it can be already unfair, meaning that the corrupt parties can get the output, but the honest parties will either get the output or not, right? So either they get the output or not. That is, all the honest parties will be on the same page. And the last one is security with selective abort. This is the weakest notion that we have here. And here it is again, it can be unfair. The adversary can get the output, but the honest parties may not. But in addition, the adversary can make some of the honest parties get the output, but some others may not, right? So the honest parties may be in disagreement. But if an honest party gets the output, that is going to be the correct output. Now it is well understood that security follows from top to bottom. That is, robustness implies fairness, that implies security with unanimous abort, and that further implies security with selective abort. And it is also known that with dishonest majority, that is when majority of the parties are corrupt, then the best security that we can achieve is security with unanimous abort. And on the other hand, we need honest majority for attaining fairness and guaranteed output delivery, which are stronger properties. And this is due to the result of CLEAN. In this work, we will focus on robustness, and consequently, we need honest majority. And the reason we settle for robustness is that a robust protocol will prevent a corrupt parties from stopping the computation repetitively and therefore upholding trust in the system. So for practical applications like PPML, it is very important to have the trust of the users, right? So this is why robustness is the best property to go for. So in summary, as far as the adversarial setting is concerned with, we settle for a malicious adversary that can corrupt minority of the parties. And as for security, we plan to offer guaranteed output delivery or robustness. Now, having the adversarial as well as the security setting in place, we will talk about the attributes that we embrace for Swift in order to make it highly efficient. Because for practicality, efficiency is the end goal. First, we work with small number of parties. Instead of working with more number of parties, we work with small number of parties. To be specific, we use 3 and 4 parties with one corruption. One corruption because we want to be in honest majority setting. Such scenarios allows for very customized and efficient solution. Secondly, we resort to pre-processing model that splits the computation into 2 phases. First, in the pre-processing phase, the computation performs function-dependent but input-independent computation. This part is relatively slow and expansive. And this is followed by the second phase, which is online phase. And this is going to be super fast because this consumes the raw data that is created in the pre-processing phase. This sort of setting fits very well for the PPML application because here we know what function is going to be computed. For instance, consider that we are interested in NN neural networks inference. In this case, we know what specific neural network inference that we are talking about. So it is not a problem if the pre-processing phase uses the definition of the function, but it is input independent. And lastly, we build protocols relying on rings, teaching field-based protocols to leverage CPU optimizations. And for our implementation, we use 64-bit rings. So towards utilizing the small number of parties, MPC with small number of parties, we use a very practically motivated model, which we call as secure outsourced computation. Here, the computation is offloaded to a set of dedicated small number of hired powerful servers. And the average end users, who could be either the data owner in case of training, or the model owner or the client in case of inference, they don't need to be computationally powerful. Then they just need to share their data amongst these hired servers, and these hired servers will perform all the computation via MPC, and the output will be finally reconstructed towards the end users. So as you have guessed, we will use MPC with 3 parties or 4 parties amongst these servers, hired servers. As far as the collusion model is concerned with, we will allow any number of end users to collude with one of the servers. Because remember that we want to use 3 or 4 PC with honest majority, where we allow only one corruption. So that is one of these servers will be corrupted, and that server can collude with any number of data owners or the end users, and we will be fine with our security. It is important to note that MPC with small number of parties is not really very restrictive. It can help solve MPC with even large population, where we can pick a representative set out of the large population, and we can run the MPC with small number of parties. It will be efficient, and we will get what we need. Okay, so we will follow secure outsourced computation setting for our protocols. Now let us move on.
Can I ask you a question here?
Yeah, sure.
When you said the data owners sharing their data with the servers, do they share this data in the clear, or is this also kind of encrypted somehow?
Yeah, this is a secret sharing scheme. So they will use some secret sharing schemes. So even though one of the server is corrupt, it will not learn anything about the individual data.
Ah, okay. All right, thank you.
So I will come to the secret sharing schemes that we use, but in general, any secret sharing with threshold 1 would work. But we come up with very specific secret sharing semantics, which would lead to very efficient protocols for PPML.
Okay, thank you.
Right. So let us now look at the 3-layer PPML framework That is, here I will capture all the primitives that PPML is built upon. So here I will be slightly broader than the scope of Swift, in the sense that this includes primitives which we have built across a few papers, not just in Swift. So therefore, some of these primitives might not have been considered in Swift. And secondly, I would again like to mention that all these primitives are realized on secret shared data, right? So the primitives will take inputs which are available in shared format amongst the servers, and the computation for the primitives will happen on those shared data. All the intermediate values will remain shared. And finally, the output of those primitives will also be generated in a shared format. And we will use, in Swift, we use two kinds of secret sharing, arithmetic and Boolean. And for arithmetic secret sharing, this is defined over a ring, Z to power L. And we use L to be 64 for our applications. And for Boolean secret sharing, we use the ring Z2, right? This is a Boolean ring. So in the very next slide, I'm going to define two secret sharing semantics that are relevant to Swift. And the boxes that are in yellow, those are the ones we have not considered in Swift. Okay, now let us look at the picture. So you can see three layers. In the topmost layer, we have put all the machine learning applications. So these are the functions that we want to compute, both training as well as inferences. We can in fact add more machine learning algorithms, but so far we are restricted to these. And neural network includes deep neural networks as well. In the second layer, we have the building blocks that lend their power to build the ML applications. So we have quite a few primitives over here. For instance, dot product, matrix multiplication, secure comparison, bit to arithmetic, bit injection, equality test, various activation functions, then oblivious selection, max and mean pool, argmin and argmax. So I'm not going to go over each one of them, but let me pick randomly one or two. For instance, dot product, it takes two vectors of same length, and each element in that vector will remain secret shared amongst the servers. And the dot product wants to compute the dot product of the two vectors in a shared format, right? Then, for instance, if I take oblivious selection, the input to this primitive is a bit and two values. And the output is the value that is indicated by the bit, right? And everything. Are there any questions?
I don't think so.
I see. Okay. So, and again, everything is, the inputs are available in a shared format, and the output we want to compute in a shared format as well. Now moving down to the layer one, here you will see the primitives which essentially lends their power to build layer two primitives. And in fact, these are the ones that are a subset of these primitives will directly contribute to a MPC protocol. Okay, so here we have input sharing, linear operations, meaning additions or multiplication by constant. Then we have multiplications to input as well as multiple input, and so on. And again, here we consider both arithmetic computation as well as Boolean computation. And in the rest of the talk, I'm going to focus on multiplication, which is the primary primitive. And also I will restrict myself to the three-party case. We have both three-party protocols as well as four-party protocols, but I'm going to talk on only the three-party case. And I'll present our protocol, multiplication protocol, which is designed in the pre-processing model that I have explained earlier. And the cost that we achieve is as follows: 3 ring elements in the pre-processing and 3 ring elements in the online phase. And this algorithm will work both for arithmetic as well as in the Boolean domain. The same thing, the same construction works. Okay, so let's move on and let's discuss the multiplication protocol. And I want to emphasize again that this is the technical core, and rest of the things actually can be built on top of the multiplication. It is used in all the layer 2 primitives. Okay, so before I move on to the multiplication protocol, as I have mentioned, our computation happens in on secret shared data, and we use two different kinds of sharings. First is replicated secret sharing, and over here the secret X is split into three parts: X1, X2, and X3. They're the additive shares of X, and every party will hold two of the shares. Right? P1 holds X1, X3, P2 holds X2, X3, and P3 holds X1 and X2. So every party misses one share, and this is the notation that we use within square bracket. This means X is replicated secret shared amongst the parties. The second sharing semantics that we use is called masked secret sharing. And here, for every secret X, there is a random mask lambda X associated with it. The mask is a replicated secret shared amongst the parties, right? This is the replicated secret sharing of lambda. And on top of it, there is a masked value mx, which is nothing but the secret plus the mask. This is available with all the three parties, with every party. And this is the notation that we use for masked secret sharing. So when you see this notation, then you know this is what I mean. There is a mask, random mask, which is a replicated secret shared amongst the three parties, and the masked value mx is available with all the three parties. There is a certain advantage in using such masked secret sharing. The mask part, all the computation related to the mask part, namely the replicated secret sharing of the mask, this is independent of the secret, the actual secret X. And this we can prepare in the pre-processing phase when we do not have the secret at hand. And if we are happy to assume a one-time pairwise PRF key setup, then in fact this pre-processing that is a replicated secret sharing of the mask can be generated for free. So, and then in the online phase, all that we need to compute is the masked value mx, which is dependent on x, right? And the invariant that we maintain for every primitive is that its input is taken in masked share format, and we compute its output in a masked shared format, right? So that nothing leaks. So for instance, for multiplication, we'll take the two inputs x and y in masked shared format, and we'll compute the product, that is x dot y, again in the masked format. Okay, so now let us move on to see how the multiplication works. So these are the input and output of the multiplication. We have masked secret sharing of x, and we have the masked secret sharing of y, and we want to compute masked secret sharing of the product x dot y, which is denoted by z. So let us expand the secret sharing, right? So x, this is the secret sharing of x, this is the secret sharing for y. These are given, and we want to compute masked secret sharing of z, which is this. And again, you can see that the replicated secret sharing of the mask of z, that is lambda z, this can be created in the pre-processing phase. This blue part can be created in the pre-processing phase. That means that computing the multiplication reduces to computing only the mz part in the online phase. Now, if you notice, mz, this is nothing but z plus the mask, the corresponding mask, which is lambda z. Now we can replace Z with XY, which is the product. And then we can replace X with the masked value, MX, minus the mask, right? And same for Y. And if you just simplify this expression, or if you just expand, then this is what you get. Now notice that we have the replicated secret sharing of lambda X, the mask of X, replicated secret sharing of lambda Y, which is the mask for secret Y. And we also have the replicated secret sharing of Z, which is lambda Z, right? So these are all available amongst the parties. And in addition, the parties hold MX and MY on clear, MX as well as MY on clear. Now, if we can compute replicated secret sharing of the product lambda X and lambda Y, then thanks to the linearity of replicated secret sharing, using this equation over here, we can actually compute replicated secret sharing of MZ amongst the parties, right? To be specific, the first party can compute the first and the third additive share of MZ. And if you notice carefully, all the first shares, the first share of lambda X, lambda Y, lambda XY, and lambda Z, they all contribute to compute the first share of MZ. This is as per this equation that we have here. And similarly for the third share of MZ, second party will be able to compute the second and the third share of MZ, and the third party will be able to compute the first and the second share of MZ. So this is exactly a replicated secret sharing of MZ. Now you can see that computing a multiplication gate, which basically requires MZ to be available amongst all the parties. MZ is nothing but the masked product. This reduces to a reconstruction of a replicated secret sharing of MZ. Right? So this is what we promised to do at the cost of three ring elements robustly, because remember that we want to give robustness or guaranteed output delivery. So we want to reconstruct this replicated secret sharing in order to complete the multiplication at the cost of 3 ring elements robustly. Now this is going to be the computation for online phase, because these are all input dependent. And I would just like to mention that in the pre-processing, the computation that we need to do is generation of the replicated secret sharing of lambda X times lambda Y. Recall that lambda X is the mask for X and lambda Y is the mask for Y. And both of them are replicated secret shared. We want to generate the product of them to be replicated shared as well. And notice that all these values, these are masks, and these are independent of the actual secrets X, Y, and Z. And all this can be done in the pre-processing phase. So our pre-processing phase will involve generating such triples, multiplication triples, right? Lambda X, lambda Y, and lambda X dot lambda Y. This is a multiplication triple, and we want to generate replicated secret sharing of them. And the reason they can be done in the pre-processing phase, because they are all lambda X and lambda Y are random values. They are completely independent of the actual secrets X, Y, and Z. This we can achieve again at the cost of 3 ring elements, relying on distributed zero knowledge. This is a technique which has been introduced in Crypto 2018 by Bonnet et al., and that had been further improved in a work by Boyle et al. In ACM CCS 2019. We tweaked their protocol in order to obtain the cost that we report in Swift. I'm not going to discuss this, and this part can be looked up from our paper. I'm going to focus on the robust reconstruction of replicated secret sharing at the cost of 3 elements, which is what we need to complete our multiplication evaluation. So let's move on. So now, if you look at the possession of the 3 parties in terms of the shares of MZ, you can see that, so this is the repetition from the last slide. First party has the first and the third share. Second party has second and the third share. And the third party has first and the second share. So each of them miss exactly 1 point. Here is a third point which is missing from the third party. Now, and in other words, you can see that every missing value is actually possessed by 2 other parties. For instance, in case of party P1, it misses the second share, and the second share is available with both P2 and P3. So this is the kind of redundancy that replicable secret sharing provides. And this is very useful when we tolerate malicious parties, because at most one of these 3 parties can be maliciously corrupt. So even though one party sends a wrong share, the other party will definitely send a correct share. And therefore, the receiving party can actually identify if something wrong has happened. Okay, so this is exactly we can do. P2 and P3, they can send across their copy of the second share of MZ to P1, and either this send will be successful, or we can actually make sure that there is a conflict revealed, and the party that lies outside the conflict will be identified as an honest party or trusted party. So if such conflicts are identified, then we also identify an honest party that is trusted. And in order to maintain robustness, the remaining computation, the computation will restart, and it will be taken care by this honest party locally. All the parties can send their inputs to this honest party, who will be able to compute the function in the clear but locally. Okay, so this is the first send that we need. P2 misses the first share, and that you can see is available with the first party over here, and as well as the third party. So they both can send the first share to P2, and again, either it will be successful or we'll be able to identify an honest party. If it is successful, then both of them has MZ, and both of them can send MZ to the third party, and that's how all of them will get MZ. Or if not, if one of the steps are unsuccessful, then a conflict will be identified, and subsequently an honest party who will be acting as the trusted party. But you can see that this naive solution takes 6 ring elements, right? Every pair of, there are 3 sends, and in every send, 2 of the parties are acting as senders. So this involves 6 elements, but I promised you to give a 3-element solution. This is where we use a new primitive, which we call as joint message passing, or JMP primitive. This is a rate 1 primitive. That means if we want to send L elements, then it will cost L elements in an amortized sense. Okay, so this is what I'm going to introduce next in order to complete our multiplication protocol with 3 ring elements. So let us see how our joint message passing protocol works. And the guarantee of the joint message passing protocol is that it will be either successful or there will be conflict identified, and as a result, subsequently an honest party will be identified who will carry out the rest of the computation locally on receiving inputs from all the parties. That's how we obtain robustness. Okay, now let us see how our joint message passing protocol primitive works. So here we have 2 senders and 1 receiver. The senders are supposed to have the same value. If they use the same value, then the receiver will receive the message, and full stop, that's it. But if the senders do not use the same value, one of them can be corrupt. So if they don't use the same value, that is M is different from M prime, then all the parties will agree on a trusted party, and the trusted party is nothing but one of these 3 parties. So they will all agree on the identity of a trusted party. So this is the guarantee we have from joint message passing, and the protocol works as follows. The first round the first sender will send the message on clear to the receiver, and the other party, other sender, will send hash of the message, not the message, but the hash of the message. Then the receiver will check hash of both the things that she has received. So she has received the message on clear from the first sender. She will apply hash on it, and from the second sender, she actually received only the hash value. She is going to compare those two values, and then she is going to set a bit B. The bit is 1 when the hashes do not match, otherwise it is 0. Then she sends across the bit to the other two parties privately, and these two parties are going to exchange the bit received from the receiver amongst themselves. And in the end of this round, you can see that every party ends with a bit. The receiver has her own bit that she decided in the previous round, and the senders also decides on a bit, and the bit is 1 if it had received 1 from one of the other two parties. That is, for instance, the first sender's bit is 1 if it has received B equals to 1 from the second sender, or the bit equals to 1 from the receiver. If either one of them are 1, then it sets the bit to be 1. And now, if the bit is 1, then all these parties are going to broadcast hash of their respective values. The first sender will send hash of its own value, second sender will do the same, and the receiver will take the hash of the message that it received from the first sender, because it has received message only from one of the senders, and the other message that it has received from the second sender is just a hash. So it's going to hash the value that it had received from the first sender, right? So these are broadcasted. Notice that if the bit is 0, that means everything is fine, so they don't do anything. But if the bit is 1, then the parties are going to take this step. They are going to broadcast the hash of the messages. Now we will identify some conflicts, and I will identify an honest, trusted party in the following way. So for instance, let us assume that, so we have several cases here. Let us assume that the sender's hashes do not match. And it is important to note that we have broadcasted all these values, so that from now on, the decision that we are going to take is going to be public. Everybody will be on the same page, because all these broadcasts are publicly known. So if the broadcast of the first and the second sender do not match, then we will take the receiver as the trusted party, right? Because surely one of them has not used the correct message. That's why they are in conflict. So the third party will be the trusted party. Similarly, if the hashes of the first and first sender, the receiver, do not match, then the remaining party, the second sender, will be identified as the trusted party. And then there is a symmetric case, and I'm not talking about that. That is dealt similarly. The last case is that all the hashes match. So this is a very intriguing case, that all the hashes match, but notice that all of them have broadcasted, meaning that their bit was set to 1, right? Which means that the receiver would have received some conflicting messages if it was honest, or if it was corrupt, then it could have sent B equals to 1, even though it has received a matching message and the corresponding hashes. But when they're publicly broadcasting the hashes, then all the hashes match. In this case, we will pick the first sender as the trusted party, because we have an argument that the first party in this case cannot be a corrupt party. Assume that the first party is a corrupt party. So in that case, the other two parties are definitely honest, and the corrupt party would have sent a wrong message M, and that is why the honest receiver would have set its bit B equals to 1, and it would have sent the bit to the honest sender, and that's exactly as the reason that it broadcasted also the hash value. If the bit was 0, then it wouldn't have broadcasted any value. Since the receiver has broadcasted and it is honest, that definitely means that this corrupt party sender would have sent a different message from the second sender. And in this case, you can see that clearly the other sender and the receiver will be conflicting publicly on their hash values, but that has not happened, right? So this means this leads to a contradiction to the fact that that we have started assuming that the first sender is corrupt. So it cannot be corrupt. So this is the reason we pick this party as the trusted party. So this is the end of the protocol, and as I had promised that this protocol either succeeds in sending the message of the senders to the receiver with a cost of the message size, because only one sender sends the message and the other sender sends only the hash of the value. Therefore, in amortized sense, the communication complexity of this primitive is size of the message. This is the cost of the message, right? The first sender sends to the receiver. The rest of the things are all on hash values, and they vanish. The cost of them vanish in amortized sense. And going back to the properties, it provides the property that either the change is successful or we identify a trusted party. Now, to further optimize this protocol and to leverage the use of amortization, we split this protocol into two steps or two phases. The first phase is called the send phase, and here only the first sender sends the message and nothing else happens. And the verify phase is constitutes of the rest of the steps that I have explained. Okay, so during our multiplication, during our computation, we can have, we will in fact have many multiplications running together or sequentially, but there will be many multiplications that we need to evaluate. In that case, on the fly, we will run only the send phase of the jump protocol, and the verify phase will be clubbed for all the multiplication together for the same set of senders. Right, so we plan to combine the verify phase once and for all the multiplication, and that's how we leverage the effect of amortization. The same phase happens on the other hand on the fly, right? And this gives us a rate 1 communication. The communication is exactly same as the message size. So to conclude or to summarize the multiplication, you can see that we had to run 3 instances of joint message passing primitive, and each one of them will take 1 element in amortized sense. So we have a cost of 3 elements for the online execution of our multiplication protocol. And as I mentioned in the previous slide, on the fly for every multiplication, we are going to run only the send phase, meaning that only one of the senders is going to send its value, and the verification of many multiplications are going to be clubbed together for the same set of senders, right? And as again, we get this property that either the multiplication is successful or an honest party will be identified as a part of the joint message passing protocol, and the rest of the computation will happen locally at that party's end on receiving inputs from all the parties. So this is how we maintain robustness. Okay, so that's the end of the technical part, and now I will briefly talk about, I'll briefly compare our work with existing works. So we compare with 2 of the state-of-the-art protocols. The first one is by Boyle et al. This is an ACM CCS 2019 paper. You can see that the protocol achieves GOD, which is same as our offer, but they have an online communication cost of 3 elements, and that's actually an overall cost. So it seems that their protocol is better than ours because we need an additional 3 elements in the pre-processing phase. But I would like to mention that the communication cost of 3 elements for them is applicable only when there are several millions of multiplications that are computed together. So that's an amortized cost, and the amortization kicks in only for a very large number of multiplications. And they also run a heavy primitive called distributed zero knowledge proofs in the online phase. This makes their online phase relatively slow. We also use distributed zero knowledge, as I have mentioned, in the pre-processing of our multiplication phase, but that is in the pre-processing phase, allowing a very, very fast online phase for us. Next, we compare with Blaze, and this protocol has exact same cost as ours, but this protocol offers only fairness compared to guaranteed output delivery. Recall that by fairness, I mean that either all the parties or none of the parties will get the output. So the adversary can stop the computation. In case it doesn't, but in that case, it also doesn't receive the message, but it can stop the computation. Whereas Swift achieves robustness or guaranteed output delivery, where the adversary cannot do anything from the honest parties getting the output. Next, I did not discuss anything about our four-party protocol, but I do. So I have the table here. Here we compare with two of the state-of-the-art works, Trident and Flash. Trident achieves fairness, and it gives the same cost as ours, but it offers fairness. And Plus offers guaranteed output delivery, the same security notion as that of ours, but it has double the cost of ours. So we have 2x improvement compared to Flash in Swift. So there are other building blocks, as I have shown you in the framework picture, the second level primitives, dot products, and many others. I'm not going into those details, but for dot product, I just wanted to give a feature that is achieved for the first time in Swift, which is feature dependence. So in Swift, both in 3PC and 4PC, we have achieved a cost that is in fact same as the multiplication, right? And there is no dependency on the feature size. Feature means the length of the vectors that we are computing the dot product of. So X and Y, these are the two vectors, they are of length D, and the cost for evaluating a dot product for Swift is 3 elements, both in the pre-processing and in the online phase, and this is independent of the feature size, and which is achieved for the first time in the literature of honest majority protocols. Even the earlier work of Blaze depends on D. So, I mean, at a high level, dot product can be viewed as D multiplications. So it is very interesting that we could get rid of D completely, both from the pre-processing and the online phase, and it has huge impact on the performance of our PPML applications. So that is all I have. And so of course we have done a lot of experiments over one and in the Google Cloud, and all those results are available in our paper. Please, if you are interested, please go over the paper and look at our experimental results. And this brings me to the end of the talk, and thank you. So I'm happy to take questions now.
All right, thank you, Arpita. Very good talk and nice delivery as well. So I think we can start having some questions if anyone has any question.
Hello.
Hi, Xinliang.
Hi. This is Xinliang speaking. Yeah, I'm also from Monash Cybersecurity Group. So thanks for the talk. Yeah, I just have probably more like a general question. So because you are adopting like 3 parties or 4 parties to do the secure multi-party computation, I'm just wondering from the high level point of view, what is the advantages and the disadvantages compared to 2-party computation? Because some like early work, they adopt like, for example, CQML, they have like 2 servers, right? So
right. Yes. And so this is a very good question. So as you know, if you work with 2 parties, then it's a dishonest majority setting, right? And we know that for dishonest majority, the protocols are typically more inefficient than honest majority protocols. To be more specific, you need cryptographic assumptions like oblivious transfer, so you cannot get rid of them. So invariably, the offline will be very expensive. So this is one reason we thought of going for honest majority. The other reason is, as I have mentioned, in terms of robustness. So we go for robust solution, meaning that no matter what, everybody will get the output, right? But when you are in the dishonest majority setting, for instance, two-party, then you cannot achieve guaranteed output delivery or even fairness. The best you can achieve is about security. So that's another reason. And we are tolerating malicious adversary. Therefore, it can happen that adversary will stop the computation, and this will reduce the trust in the system. So this is why we believe that robustness is a very attractive feature, and practical applications should go for that. And for that, we necessarily have to go for honest majority. So after two, the next best case is three parties, right? So this is why we settle for three parties with one corruption.
Okay, thanks. Thank you. Thank you for the answer. Thanks.
All right. Any other question for Arpita? Maybe I ask another one. So
Sure.
Arpita, can you go back a couple of slides back once you were comparing the number of multiplications that you had? Yeah, for example, here, you mentioned that the first scheme by Edith Boyle, it's only achieving these three online elements if the number of multiplications is huge, right?
Right.
Yeah. So have you done like the experiments to see where exactly these like where is the threshold happening? Like after 1,000,000 multiplications, is it 1,000? And have you compared it with Swift, like numerically?
Yeah. I think we did it, right? But so the parameters that you have to set for the distributed zero knowledge is I mean the amortization kicks in for a large value. I don't have the exact figure, but I think we have the number in the paper that that shows that for exactly how many multiplications you can achieve 3 elements per multiplication, and that's quite huge. Even comparing applications like neural networks, which already have like many kits, it's still huge for such applications. And since this is a one-shot protocol, I mean, they don't have pre-processing or online. This is one-shot protocol. They have to run this distributed zero knowledge during the online phase, and which we think is not ideal, for instance, in case of inference, right? When we offer machine learning as a service and we take inference as the example, you would like quick delivery of the output, right? And in that case, I guess the online phase should be extremely fast. And the distributed zero knowledge, at some part, they have to go for extended rings. The rings were quite big in that case, extended rings. And that part of the computation is relatively slow. It's expensive and therefore relatively slow. And that makes the online phase very slow. So we wanted protocols which would be really suited for practical applications. I mean, you give the query and you get the output immediately.
Okay, fair enough. Any other question? From the attendees? No. Okay, if there is probably no other question, we can conclude this session. And I just wanted to, if you kindly stop sharing, I just wanted to share the
Sure.
a slide for the next presentations, if I can do it, because it's usually done by Mohammed. So let's see. Okay. Yeah. Anyway, thanks again, Arpita. That was quite a nice presentation.
All right.
Yeah. And,
Thank you.
Okay, I cannot open it. Okay.
All right. So I will lead the meeting.
Yeah, please. Oh, okay. It came up. Just came up. Yeah. Thanks again, and hopefully we can have you again for some more fruitful research. Yeah.
All right. Okay.
Yeah.
Bye.
Bye bye.